In this lecture, I want to introduce Bayes networks or Bayesian networks. These are important tools that are used throughout artificial intelligence and machine learning. And these tools help to capture certain patterns of causal reasoning. Now, it's a big topic, and we don't have time to discuss everything about this topic, but I can give you the basic idea of how Bayes nets work and how you use them to capture certain patterns of reasoning. So I want to start by talking about independence and correlation. Phi and psi are said to be independent when the probability of phi given psi is equal to the probability of phi. And of course, that will also mean that the probability of psi given phi is equal to the probability of psi. When this happens, when the probability of phi given psi is equal to the probability of phi, that means learning something about psi doesn't tell you anything about the other formula phi. And similarly, learning something about phi doesn't give you any information about the formula psi. And that's what it means for phi and psi to be independent. The other hand is phi and psi are correlated. And if they're correlated, that means the probability of phi given psi is not equal to the probability of phi. So learning something about psi will raise or lower the probability of phi. There might be a positive correlation in the sense that learning psi might increase the probability of phi, or a negative correlation in which learning psi might lower the probability of phi. Now, with these definitions in mind, let's talk about Simpsons paradox. Recall that Simpsons paradox is a situation where there's an event C that seems to increase the probability of E in a given population P, and yet at the same time decrease the probability of E in every subpopulation of P. So in other words, suppose that we have two complementary propositions, F and not F. So some people in the population P satisfy F, and the remaining satisfy not F. Now we might encounter the following inequalities. 1, C raises the probability of E, or rather, the probability of E given C is greater than the probability of E given not C. That means if C is true, the probability of E is higher than in situations in which C is false. Second, if we restrict attention to all the people that satisfy F, then C being true actually lowers the probability of E, in the sense that the probability of E given C and F is less than the probability of E given not C and F. Third, if we restrict attention to all the people satisfying not F, then again, C lowers the probability of E, in the sense that the probability of E given C and not F is less than the probability of E given not C and not F. And so this is puzzling. Although such order reversals might not surprise students of probability, it does appear paradoxical when giving a causal interpretation. Because if we think that 1 signals the fact that C is causing the probability of E to increase, then it's very puzzling why it no longer has that causal effect when you restrict attention to each of the subpopulations. Now, modern analysis explain away Simpsons paradox by distinguishing seeing from doing. So here's the key idea. This conditional probability, the probability of something conditioned on C, this means that given that we see C, and it should not be used to compare, say, effects, impacts, harms, or benefits. So, in other words, the probability of E given C is greater than the probability of E given not C. This is not a statement about C causing the probability of E to raise, or about C being a factor contributing to E, but rather it's a statement about C being evidence for E. And this may be due to factors that cause both C and E. Now, here are two books that go into further detail about this way of thinking. Judea Pearl is the main figure who has developed these ideas. He's a very well-known computer scientist, and he did a lot of the foundational work to develop the ideas presented in this lecture. In particular, the second book, The Book of Why, is a very good popular book aimed at popularizing some of these ideas. Now we're ready to define a Bayesian network. A Bayes network is a directed acyclic graph, I'll say what that is in just a second, with a probability distribution respecting what's known as the Markov condition. And I'll also say what that is in just a second. So an acyclic graph, this is just a collection of nodes. So here we have 1, 2, 3 nodes, and they're labeled with C, X, and Y. We think of those as propositions or events. And it's a graph when there's an arrow from between the nodes. So there's no arrow between Y and X or Y and C, but there is an arrow from C to X. And it's acyclic means that there are no cycles. So a cycle would be something like if you have A pointing to B, B pointing to C, and then C pointing to A. So this is a cycle. Being acyclic means you don't have anything that looks like that. And it has a probability distribution respecting what's known as the Markov condition. And I'll say what that means in a second. But basically the idea is that when there's an arrow from C to X, that means that X depends on C, or that C is somehow causing X. But if there's no arrow between the nodes, that directly between the nodes, that means that those nodes are independent. So the probability, in this example right here, the probability of Y and X are independent, but X depends on C. Now, before I talk about how you infer probabilities given a Bayesian network, I want to introduce some notation and remind you of some basic facts about probability. First of all, if we write the probability of P comma Q, when you see that inside of a probability distribution, this always means the probability of P and Q. It just simplifies the notation a little bit. So P commas really are interpreted as conjunctions. So the probability of P and Q is going to be equal to the probability of P times, well, it's not the probability of Q because P and Q may not be independent, but rather it's the probability of Q given P. And so remember, this is going to be the probability of P times the probability of Q and P divided by the probability of P. So the probabilities of P cancel. So that's where you get this equation. But if P and Q are independent, then of course the probability of Q given P equals the probability of Q. And this can just be simplified to the probability of P times the probability of Q. Now, if you have 3 propositions, P, Q, and R, and we want to know what is the joint probability of P, Q, and R, that is, the probability that P is true, Q is true, and R is true, well, this is going to be equal to the probability of P, not times the probability of Q, because we don't know if P and Q are independent, but rather the probability of Q given P, and then it's times the probability of R given P and Q. So to see why this equation holds, note that the probability of Q given P is the probability of Q and P divided by the probability of P. And the probability of R given P and Q is the probability of R and P and Q divided by the probability of P and Q. And this is all multiplied by the probability of P. And now we can see that the probability of P's cancel, the probability of Q and P cancels, and we end up with just the probability of R and P and Q, which is, of course, just the probability of P, Q, and R. Now, we already know that if P and Q are independent, then this middle term can be simplified to just the probability of Q. What about this last term right here, which is a bit more complicated? This is the probability of R given P and Q. Well, we also have a notion of conditional independence. R might be independent of Q given P when the probability of R given P and Q is equal to the probability of R given P. And it's this information about which propositions are independent and not independent is what is captured by the Bayesian network. And when you have three propositions, there are three typical examples. You might have a chain of events, so P causes or contributes to the truth of Q, and Q contributes to the truth of R. So you might think of something like R is an alarm going off, so it's true if the alarm is going off and false otherwise. Q is there is smoke in the room, and P might be there is fire. So if you hear an alarm, the alarm was caused by smoke, but the smoke, what caused the smoke is fire. So hearing the alarm gives you information about the fact that there's a fire, but it's only indirectly through this middle variable, the smoke variable. There are other relationships between three propositions that are important. One is both P and R might cause Q, and the third is there's a common cause. Q causes both P and R. And I'll talk about these other two in just a second.